Hello guys, and welcome back to my video series for applied machine learning. Today we'll be continuing with our problem for detecting fraudulent transactions using machine learning. So as you can remember from the previous video, 99% of we're given an imbalanced data set in this problem. So we have 99% of the data consists of non-fraudulent transaction, whereas the percent of the data set is fraudulent transactions. So if you can remember from the previous video, we solved this issue by creating a subsample which is equal number of fraudulent and non-fraudulent transactions. So we use this by using random undersampling technique. So a random undersampling technique is we remove more features from the class. We remove features from the class with more data set than the other, so that the data set becomes equal. So in this video, we are going to interpret the data. We are going to interpret the data that we are given, and we are going to see the correlations between the data in the type of problem which we are going to solve, which is to detect if a transaction is fraudulent or not. So when we want to see the correlation between our data set, we use what we call correlation matrices. So the first correlation matrix that we are going to create is the correlation matrix for the entire data set. That is the data set which contains both fraudulent and non-fraudulent transactions, and which is the data set which is imbalanced. So this is the data set which is imbalanced. So here the correlation, which is df, which is the data frame that we created in the beginning, is dot correlation. This method is the method we are going to use to create our correlation matrix. And then we then use the seaborn library .heatmap. We pass in the variable that we created here. We pass in the cmap, which is coom, and then we pass in other arguments, and then we set the title is imbalanced correlation matrix. And then for this, and then the second correlation matrix is the correlation matrix of our subsample. Our subsample, which we created using random undersampling technique, which is equal number of fraudulent and non-fraudulent transactions, right? So if I run the code, you can see here, because our data set is highly imbalanced, this affects our correlation matrix. As you can see, our correlation matrix is not showing us much information for our data set with imbalanced, for our data frame with imbalanced data set. But if we check at our correlation matrix, but if you can check from our correlation matrix that we created using our subsample data set, which we created from the random undersampling technique, you can see that this gives us much more information. So as you can see from here, from 0 to 0.8, these are positively correlated features. From here 0 to negative 0.8, this shows negatively correlated features. As you can see, V1, we have this blue color. As you can see, it's around here, which shows that V1 is a negatively correlated feature as to our class, as compared to our class, which is fraudulent transaction, which is equal to 1, which is. So as I was saying, the more negative our value, the more negative our value, the more likely that it will be a fraud transaction. And then for positively correlated value, the more positive our value, the more likely that it will be a fraudulent transaction. So the next thing we are going to look at Boxplots. So what are Boxplots? In statistics, Boxplots show the distribution in our data set. In Boxplots, we have the upper part, we have the upper value, which shows us the highest value in our data set. We have the upper quartile, which is 75% of our data set. We have the lower quartile, which is 25% of our data set, and then we have the lowest value, which is the lowest value in our data set. And then the values that are beyond the lowest values are called the outliers, and the values that are above the highest value are called the outliers. and then this part shows us the median. So as you can see, we are going to plot box plots so that they can show us how the distribution of the negatively correlated classes of the negative correlated classes against our class, which is the fraudulent transaction. So as you can see, these are the box plots showing the distribution of our negatively correlated features in our class, which is the fraudulent transaction. So the same goes for positively correlated features. And then our next step, we are going to look at the anomaly detection. As I was talking about, box plots show us the distribution in data, but the most important thing, they show us outliers. So as I was speaking, that outliers, the values that are beyond the highest value in the box plots are called the outliers. The values that are below the lowest point in the box plot are also outliers. So we have to remove outliers. We have one important concept, which is the interquartile range. So we calculate the interquartile range by the difference between the upper quartile range, which is 75 percentile, and the 25 percentile. So our aim is to create a threshold beyond the 75 and the 25 percentile, that in case in some instances you may play around with this threshold, but since we don't want to remove all of the outliers, so because we may lose some valuable data that will affect the performance of our algorithms, right? So the in this case we'll be using 1.5, but you can use a higher threshold. But the higher this threshold is, the less outliers will detect, and the lower this threshold is, the more outliers it will detect. So we need sort of like a trade-off. The lower the threshold, the more outliers to remove. However, we want to focus on extreme outliers. So we want to focus on the values that are beyond the highest value, and the values that are below the lowest value, because we might risk losing information that will cause our models not to perform well. So as you can see, to remove these outliers, the first thing we do is we create a new data frame, which is the V14 feature fraud data frame. Is equals to new data frame. We pass in the column number, which is V14, and then we pass in new data frame class is equal to 1. So we want to select feature values where our class is equal to 1, which is the fraudulent class. Since our main aim is to detect fraudulent transaction, we then convert these values into arrays by using the dot values, and then we create the Q25 value, which is the lower quartile, Q75, which is the upper quartile. We then use the NumPy library for np.percentile. So np.percentile V14 fraud, using our new data frame that we created, and then we pass in the 25 value. So what this piece of code does is that it selects the lower quartile for our data, and then the np.percentile V14 fraud, we pass in the new data frame that we created above, pass in 75, which is the 75% of our database, or of our data set, which is 75% of our data set, and then we print in the 25, the lower quartile, the upper quartile, and then we pass in the variables Q25 and Q75, and then we want to find, as I was saying, the most important concept when you want to remove outliers is the interquartile range. So to calculate the interquartile range for V14 feature is equal to the upper quartile, which is Q75, minus the lower quartile, which is Q25. We then print in the interquartile range to cut off the outliers. Remember, we would multiply the interquartile range by 1.5, and then we have V14 low, which is lowest value, V14 upper, which is the upper value, So here V14 lower, we want to remove the outliers that are lower than the lower quartile, which is Q25. We say Q25 minus V14 cutoff. This will show us the lowest value, and then the lowest value in our data set, and then Q75 plus V14 cutoff. This will show us the values that are more than the values that are more than the upper quartile. We print the cutoff V14 lower, V14 up, and then to remove the outliers, we say outliers. We'll create a variable x for x in V14 fraud, which is our data frame that we created at the beginning. If x is lower than V14 lower, that means if x is lower than the lower quartile or the lowest value in our data set, or if x is greater than the upper quartile, or if x is greater than the highest value in our data set, we print feature V14, we print the outliers. So this will print the outliers, and then print V14 outliers. So now this part is where we remove the outliers. So create a new data frame. The new data frame is equals to, we then use the pandas library function, which is the drop. We are going to drop in our new data frame every value that is greater than the V14 up, any value that is greater than our highest value, or any value that is greater than, that is lower than our lowest value. So that's how we remove the outliers. We then print the outliers. The same goes for fit-curve, removing outliers for our feature number fit-curve. We do the same process that I've said above. We create V14 fit-curve fraud, a new data frame fit-curve. We pass in the column number. We select the class which is equals to 1, since we are only more focused on fraudulent transaction. We convert this into array using the dot values, and then the lower quartile, which is Q25, upper quartile Q75, is equal to np dot percentile using the numpy library to perform mathematical function, statistical function. np dot percentile fit-curve. We then pass in the entire data set, which is fit-curve fraud. We want the 25% of the data set, which is the lower quartile. We do the same here. We want the 75% of the data set, which is the upper quartile. We calculate the interquartile range, which is the upper quartile minus the lower quartile. V cutoff, which is equal to interquartile range for our fit-curve feature multiplied by our threshold, which is 1.5, but you can change this threshold and you can play around with this threshold. Fit-curve lower, fit-curve upper is equals to the lowest value in our data set is the lower quartile minus fit-curve cutoff. The highest value is the upper quartile plus fit-curve cutoff. We then print these values. We then loop in our data. We first create our variable x, and then loop in for this variable x in fit-curve fraud if x is less than fit-curve lower, or if x is greater than fit-curve upper. We then print in the outliers, printing the fit-curve outliers for fraud cases. Then we create a new data frame without outliers. In this data frame, that's where we cut off our outliers. New data frame is equals to new data frame dot drop. We drop in all values that are greater than our upper quartile, or all values that are lower than our lower quartile. We then print in this value, as you can see. And then, as you can see, we do the same for feature V14 feature fit-curve, and then we print these box plots again. As you can see, if we print these box plots again, you can see now that we have a few outliers, as we did not remove all outliers, but as you can see now, we don't have as much outliers as before. So thanks for watching, guys. I hope this video helped you understand how we can see how our data is correlated and how can use Boxplots to show us the distribution in our data set. So in the next video, stay tuned for the next video. In the next video, we'll talk about principal component analysis and other dimensionality reduction algorithms such as t-SNE. Thanks for watching, guys. Cheers.